Okay, love this topic. Proof by mathematical induction, PMI. So PMI, it's just a way of proving certain patterns that we see. We're going to start off by looking at a variety of series, and we should recognize our symbol here for the sum that we looked at with sequences and series, but we looked at arithmetic and geometric series, and we could find rules for those, and you know that worked. So now what we're going to look at is what happens if they're not arithmetic and not geometric, and if we're told that it equals this rule, then can we prove that that will work for all values of n? Okay, and how do we do that? Well, we could go through and just, you know, choose random values. So what if we go, will it work for when n is 2? So when n is 2, we're looking at the first two terms here. So the left-hand side is going to be 1 squared plus 2 squared. Right, and we can see that, yep, that's 5. The right-hand side, when n is 2, so this becomes 2 times, now 2 plus 1 is 3. 2 times 2 is 4, plus 1 is 5, and we're multiplying there, not dividing, and divide by 6. Okay, so 2 3s are 6, divided by 6, they cancel, and we get 5, and it equals our left-hand side. Now, do we do this again for n is 3, n is 4, n is 5, and we keep proving that it works? How far do we have to go before we go, oh, well, that's enough, yes, it works for all? And do you know what? It's never going to be enough. So we want to come up with this process of how can we prove nicely that it will work for all of them. So what we're going to do is we're going to say, well, look, if we can assume, so we'll assume that it works for this random value, or whatever we go up to. So let's say k. We're not choosing n because n is our last term. So if we can assume that it works for the kth term, so let's imagine k was 5, we assume it works for 5, we're then going to say, can we use this statement here? Can we use it to prove that then the k plus first term will be true? Because what we then have is that, okay, if you've got this first term, the next term works. And that means we can say right at the beginning, well, it's going to work for the first term. We've proved it works for the first. It's going to work for the second, third, fourth, and so on. So that might sound a bit crazy, but we'll show you how we do it. And everything that's in blue, we need to write that down for every one that we do. Okay? So we're going to start by proving that it does work for the first term. Now, this, remember, recall, that means that n is any positive integer. So that means 1, 2, 3, and so on. So, does it work for P1? So our left-hand side is 1 squared, which is 1. You need to show that it works for your right-hand side. So that's going to be 1. 1 plus 1 gives you 2, right? 2 times 2, we just did this before. 2 times 1, sorry, is 2, plus 1 is 3, all over 6. And we can see that that does indeed equal 1. So that equals our left-hand side. And we write, therefore, P of 1 is true. The next thing we do is we are going to assume that PK is true. So we are going to assume, to write this down now, we're going to assume that 1 squared plus 2 squared plus 3 squared all the way up to k, the kth term. So k squared, we're assuming that that will indeed, when we pop that into our pattern, so all we're doing here is we're replacing n with k. We're not using n because that means it's our last term. So we're just saying this is some random term, k. It could be the 5th term, it could be the 8th term, etc. Okay, and now what we want to do, our job, is to prove that k plus 1 is true. so the k plus first term. So we go back to our thing up here and we go, okay, it's 1 squared plus 2 squared plus. Now instead of just going straight to the k plus first term, I include my kth term. Okay, and then we've got the k plus first term would be k plus 1 all squared. Wherever n is, replace with k plus 1. And now our right hand side, instead of n, it's now going to be k plus 1. And instead of k and n here, n plus 1, it's k plus 1 plus 1. So it becomes k plus 2. And 2k, so just be careful here, it's 2 times k plus 1 and then plus 1. So this becomes 2k plus 2 plus 1. So that's 2k plus 3. So not a lot of thinking there. It's just sort of regurgitating and substituting in. So here we go. We want to prove, so here comes the proof. We're going to go left-hand side. Now I hope you agree that all of this here, that equals this. Which means I can replace all of that with what we said P of k is. That's exactly what we're going to do. So all of that we're replacing with, that is actually k plus 1, 2k plus 1, all over 6. And let's not forget our k plus first term, so we have to say that's plus k plus 1 squared. Right, so again, not much has been done. We've just been substituting. What our job is now is that all of this, we want to prove that it is equal to this. So away we go. We are happy to add fractions. Right, we go, yep, we want to get the same denominator. So this is technically a 1 there. To get the same denominator, we're going to multiply them together, so it's 6. What did I have to times this side by to get, so this side to get the 6, or just 1, so we keep that as k plus 1, 2k plus 1. What did I have to times the 1 by to get to 6? So I've got to do the same to the top, so that becomes plus 6, k plus 1 squared. Please keep your eye, remember, on what it is that we are trying to make it look like. Okay, so you're trying to make it look like this up here. Now things are quite good because we've got the 6, but look at their top line, right? That doesn't look like ours. But can we see that we have a common denominator? Because the last thing we really want to do is expand all of that. Crazy. So here we go. We're going to pull out our common denominator of k plus 1. Right? Sorry that I keep changing colours, but I'm hoping it will be helpful to you that you can see. So now I'm pulling out this, just put that there so I don't have to keep changing the colours on you. When I pull out this k plus 1 from here, I'm left with the k, and I'm left with the 2k plus 1. And when I pull out k plus 1 from here, remember k plus 1 squared is k plus 1 times k plus 1, so I have a 6 times k plus 1. Don't forget that 6 is being multiplied by all of them out the front. Okay? So remember, keep your eye on the prize over here. And we are now keeping that k plus 1 out the front. We're going to expand inside the brackets, and hopefully it's going to equal this bit here. All right, so here we go. K times 2k is 2k squared. K times 1 is k. Then we've got a 6k plus 6 all over 6. We've got k plus 1, 2k squared plus 7k. When we see a quadratic, I hope that we are just itching to try and factorize it. Okay, we have k plus 1. Now, there's no common factor of 2, so it has to be 2k times k. To be honest with you, all right, if you have trouble with factorizing these quadratics with the thing at the front, well, I'd say practice. But remember, you've actually got your answer over here. But we're going to do it old school, and we're going to go, yep, let's see if we can factorize without looking at our answer there. So what two numbers times together give you 6? 1 and 6, and 2 and 3. Clearly, if I put a 6 here, I'm going to get 2 6s are 12. That's not going to get me the 7 in the middle. And if I put the 1 there and the 6, it's still not going to get it for me. So let's try. Oh my goodness, 2 times 2 gives you 4k. And if I put the 3 here, 3 times k gives me 3k. 4k plus 3k is 7k. And lo and behold, that is our answer up here. So we can say with confidence this equals our right hand side, and therefore we have proved it. Now, to make sure that you get all of the marks that are owing to you, you must finish off with the statement. Now it sort of goes here, but because I've run out of room, I'm going to put it up here. And your statement is basically summarizing everything that you've done. So everything in blue that we did here, we're now going to summarize. So the first thing we did was we proved that P of 1 was true. So that's exactly what we say. We say since P of 1 is true and P of k plus 1, we proved that that was true. P of k plus 1, oops, should have put is there anyway. P of k plus 1 is true. But remember, we only used that, right? We only did it by assuming P of k is true. And so back up here, right, you must put using pk. I forgot to do that at the beginning, so always make sure that it's there, right? So because we substituted pk in here, you've got to put this statement. So back to our what we're saying here, since P of 1 is true and P of k plus 1 is true, whenever, right, whenever pk is true, because that's what we did, then Pn is true for all positive integers. And why did we do this? We did this by using mathematical induction. So proof by mathematical induction. Bang. Okay. So remember, what we did was we proved that, right, if this term, the term before this one is true, then we can prove that the next term is true. Then that means the next term would be true, and the next, and the next. And because we started by proving P of 1 is true, then the next term after that is P of 2. So that has to be true. And then the next term after that. So it keeps on going, and that's how it works by PMI.